equipment which measures deformation, and I'll talk a little bit about that a little bit more later. We have seismometers that measure earthquakes, and then we also have a temperature sensor at the hot spring. And so the importance of using different techniques is you don't want to put your money on one horse, right? So you're spreading on all these different techniques because each of them may give you different warning signs if a volcano starts to reactivate. And therefore it's very important and essential to actually use different techniques to monitor the volcano. So a little bit more about the GNSS. So GNSS stands for Global Navigation Satellite System. It's complicated words, but I think many of you may have used the same technique actually on your phone when you're trying to navigate somewhere, right, and trying to find something. So the way it works is we have an antenna installed, and the antenna receives signals from all these satellites. It used to be that it was only GPS, the American system, that we would receive, but nowadays there's many satellite systems. So there's also European Galileo, and there's also a Russian system. So we receive all these signals from all these different satellites. And with that, we can very precisely calculate the position of a point. And that's important because if the volcano swells, if you have your instrument on the side, then basically the instrument will move, and so you can measure the swelling. The antenna is connected to the receiver, and then the data go directly to our institute 24/7, where they're analyzed then further. So what we measure with it is the volcano deformation. So it's the change in the size, the shape, or the volume of the volcano over time. And we can actually measure it with this technique with millimeter to centimeter precision. That's especially crazy if you realize that these satellites, they're orbiting the Earth at 6,000 or 7,000 kilometers. Still, we can get to millimeter, centimeter precision on the Earth. So this is actually the antenna that we have at St. John's. So tomorrow we'll be doing an excursion there. So I believe there's still free spots. So if you still want to sign up, go and see Emily or JJ or Joe at the tent, and you can come and see what we're doing right there at St. John's. So this is what the data look at. Looks like maybe a lot of weird dots to you. Let me explain this graph a little bit. So on the axis here, that's just the movement in the change in millimeters. Here on the horizontal, we have the time. And then basically each day we create a dot like this. And then you can see that there's sometimes a dot a bit off the track. That's normal, that's nothing strange. What we look at really is this trend. And you can see each panel is a different direction. So we measure in three components. So the top panel is the north component. The bottom one is east, and the middle one is east, and the bottom one is the up component. And you can see that the whole island basically is moving towards the north and towards the east, so towards the northeast. Now, does that make sense? Yes, it does, fortunately, because if you look back at the plate tectonics, right, Ceiba is on this side of the Caribbean plate, and the whole Caribbean plate is basically moving towards the northeast. So what we see in the data is basically normal plate motion. Now, if the volcano were to do anything, right, what we would see is a clear deviation from the trend. So the whole thing would start to go in the other direction. And of course, because you're measuring in three components, it would even show a deviation at the same time in different components. And it would most likely start to show it first in the north and the east component, and then in the up component, because that one, as you can see, it's more difficult to actually get very accurate results on, and that has to do with the satellites, the height of the satellites, and seeing them low on the horizon. So it's definitely if you see a deviation in the trend, then we'll know that something is going on. And then I think it's your turn, right? Because we'll go to seismology, and he knows much more about seismology than I do.
Good, thank you. So this microphone is also working, huh? You can hear me? Good. Indeed, we switch now to seismology, which is the science to monitor earthquakes. So earthquakes do occur when the stress in the subsurface is too high for the rocks to stay in place. So if the stress is too high, there will be a sudden break in the rock and it will release energy, and that is essentially an earthquake. So also within volcanoes, when there is a change inside the volcano by, for example, movement of magma or even by cooling down of the system, there can be a change of stress in the underground that may create earthquakes. So it's important to use instruments to measure the earthquakes, and that is what we do with seismometers. So on the right you see an example of such a seismometer, which basically is a sensor and sensing device which measures the movement of the ground. It's a very sensitive instrument, and it is connected to in this case the orange box that is making a digitized signal from the analog signal coming from the sensor, and sends that also by internet in real time to KNMI. So we have a monitoring system that automatically analyzes all the data of the seismometers to detect earthquakes automatically and do the calculations also automatically. It is, as I mentioned, a very sensitive device. You can see it measures velocity changes up to 1,000 of a millimeter per second, and that is really very special. So is there a difference between volcanic and what we call tectonic earthquakes? In principle there is, although the mechanism of course is that the earthquake is a break in the system when the stress in the subsurface becomes too large. But in the tectonic case, this is driven by the movement of the plates. So within the plates, existing faults may shift because the stress is too large. In the case of volcanoes, it might be the case that moving magma may change the stress and induce earthquakes. So there is a difference in the underlying mechanism that may create a tectonic or a volcanic earthquake. You can see, for example, on the cartoon on the right that there are faults in the system under the volcano, and by moving magma the stress may change so that existing cracks may be activated and there may be a earthquake on that specific fault. And then on the next slide, here you see different types of volcanic earthquakes, and in particular, and that is important for us to look at the signals, there is a difference also in the signature of the earthquakes that we monitor. So in the first case on top, it's what we call volcano tectonic events, and these are what we call regular tectonic earthquakes that we see, and they are characterized by a primary wave and a secondary wave that we can see clearly on the signal. And this is basically a type of signal that we see in many situations, and also in volcanoes. So they are due to stress changes in the volcano and the cracks that are in that zone. So the second one is a different type that is more related to the movement of magma or fluids into the system, and that may cause what we call long period signals. You can see that the signature is different from the one on top. It's more what we call long period waves. It moves more slowly in time, so it has a different signature. We can recognize that as seismologists. And the last one on the bottom is what we call tremors. These are continuously oscillations, and they are really caused by movement of magma into the system. So if we look at the three signals from top to bottom, we can see that if we go down, there will be an increase of activity. So if we see, let's say, the first type of earthquake types, we are not worried because it can have different causes, and as long as we don't see the long period of the tremors, we are feeling safe.
And these bottom twos we've never seen yet.
Those we have never seen on Seba. So it is very quiet at the moment. Thank you. I also want to express a little bit the difference in the types of waves that can travel through the Earth, because it's very important for seismologists to understand the features, because then we can also understand the types of earthquakes, and we can use the features also to locate earthquakes on the Earth. So the first two types is what we call body waves. They travel through the Earth. They really go inside and turn back to the surface, while the last two ones are what we call surface waves, and they really travel along the surface of the Earth, and they have also, for example, different speeds. The waves, they travel with different speeds through the Earth or alongside the surface, and we use these types of information again to characterize and to understand our seismogram and to understand the type of earthquake. The next slide is an example of an earthquake. As I mentioned before, we have the P wave and the S wave. They have different movements inside the Earth. The P wave is the fastest. It has the highest velocity. So it's the first arrival on the seismic recording. It's very important to know that time exactly, because if we then combine the arrival time of many seismometers, we can locate the earthquake. We can calculate the location of the earthquake. S waves are very important also to determine the depth of an earthquake. So it's very important also to try to see if we can find such an S wave in our seismograms. Also, it is very important to notice that the sensor, as I mentioned, it is a sensing device in three different directions. So the vertical, northeast, and north, south, east, west, and that is also important to help us to understand where the wave is coming from. Next, please. This one here. So, as I mentioned, the time difference between the P and the S is very important because they travel with different speeds. So, if we have an earthquake and you have your P wave traveling and your your P wave traveling and your S wave, the longer the time takes, the difference will be larger. So we know that for a large difference, the location will be further away. So in this case, if we look at the station with the travel time 2t, T2, we can determine between the P and the S phase. We know that the earthquake location is somewhere on the circle. For another station, we measure a smaller time difference. We know that the circle, so the distance, is smaller. So if we make that circle, we have two intersecting points where the earthquake can happen. So we need at least a third station where we also determine the difference in time between P and S, and we find then exactly where the earthquake is. With more stations, we can do the calculations more accurate, and also we can find the depth better. So we need more than 3 stations, which is the case also on the island here. We have 5 seismometers. 5. So on the next slides, this is what I mentioned is the theory. In practice, we have a very dedicated piece of software that receives the data in real time 24/7, and it is analyzed automatically to detect such kind of events, so PNS phases detected automatically. We also make use of data from neighboring countries, from neighboring islands, because seismology and also GNSS is open data science. We do share data internationally as much as possible. So we have access to many, many more stations and data in the surroundings, which helps us to locate regional events, regional earthquakes around Ceiba and St. Eustace. So the next slide is, for example, the outcome of such an automatic process. And in this case, this was an earthquake which is about 100 kilometers east of Ceiba, with a magnitude 4 at a depth of about 22 kilometers. You can see on the right top diagram, you can see the arrival times of the seismic wave as a function of distance. So the further you get away, the later the arrival time of the seismic phase. So this is very useful for us to analyze all the data that flows in automatically 24/7. The next slide is then the outputs. What do we do with the data? This is the surroundings of St. Eustace and Ceiba, where every circle is an earthquake that is detected by our network in the last 3 years. So the color coding is for the depth. So we can see that many of the events, the earthquakes, are red, which means they are not so deep, between, let's say, 0 and 50 kilometers, while more greenish ones are the ones that are deeper, between 100 and 150 kilometers. So what is interesting to see here is that if you go from the subduction zone to the southwest, you can see that the earthquakes are going deeper, which is in line with the subduction zone that we have in this area. So if we go to the next slide, we have the same picture, but now for 20 years of data used by the International Seismological Center. It is an international center where all information is used for science, for research. And you can see here that the earthquakes are really following the line of the subduction zone. It really follows the curve exactly. There is, however, a gap. You can see Ceiba and there is a little bit of gap, and that is why our network here is so important, to fill that gap also for the regional earthquakes, and to make sure that the international database is complete with this information. So the blue lines you see are a profile that are depicted on the right. So if you follow the line and you look into the depth, you can see that the earthquakes, they follow very nicely the subduction zone in both profiles. So this is very nice to see that the subduction zone here is real and it causes earthquakes up to a depth of about 200 kilometers and sometimes more. Very nice. The next is just a slide I want to share with you, because I spoke about surface waves. And surface waves are very interesting, because if you have a large earthquake, it can cause surface waves that travel from the earthquake to the monitoring sensor, but it can also go further alongside the earth and be noticed again on the seismometer sometimes later. So in this case, we have an earthquake. A surface wave travels to the station. It's what we called R1. At the same time, a surface wave travels back in the other opposite direction and arrives at the seismogram. It's what we call R2. But if it's a very strong earthquake, it can go again to make another round alongside the Earth surface. So if we go and look at the seismograms, for example, here, these are recordings from all the stations we have deployed here in this area. So on top we have the Seba stations, and then on the lower part, the ones on St. Eustace and even one on St. Martin. This is for an 8.2 magnitude earthquake in Alaska last July. And because it was so large, there was a lot of energy released that traveled alongside the surface of the Earth. So the first arrival, the R1, is very good visible. Then the opposite wave, the R2, is arriving there, very, very visible. The R1 goes back one more time, and we see it as R3. And so we can identify also the R4 and the R5, and we're talking here at a time of about 9 hours. So what means that a really big earthquake can be visible for a long time by these very sensitive instruments. I think that's very interesting. Yes, and then the next slides, Elske showed that we are doing also temperature measurements in the hot springs. So this is what we have on the hot spring opposite Green Island. You can see in the red circle where it is, and you can, if you're there, you can really feel there is hot water coming out of the ground, and you can. It's pretty warm. You can really burn your hands. It's not good to put it inside for a long time. So we put in temperature sensors, and to protect it from washing away by the sea and to really keep it in place, we used a fishing net that we filled with rocks to keep that in place. So beneath the fishing net, there are two sensors inside the hot spring that are connected to a data logger there on the rock. It's a very interesting exercise to make some instruments there and to keep them in place. But we have been successful, and the next slide, this one, will show you some results at the end of 2018 until 2019. And what you can see is there is a lot of fluctuation in the temperature. But there's also a more or less stable level on the high side. We measure at maximum around 82 degrees, sorry, and that is very stable over time. So we know that the temperature is not increasing. The fact that there are so many fluctuations is by the tidal effect. There is cold seawater flowing in, and that of course drops the temperature. And if we do analysis of this, we can really see the tidal effects very, very, very clearly. It's amazing. But important for now is that the top level is very stable. There is not so much variation on the temperature on the high side. And this is the last slide I will show, and then Elske will take over again. This is for the network, the current network. So the triangles are colored here to indicate what types of instruments we have. The ones in red are the ones with a seismometer only. So there's one in the bottom and one on windward side. The ones in blue are seismometers and the GNSS sensor. So we have one on Seba in St. John's, and another one at the airport on the north. And the new one we recently installed is the green one, also a seismometer and a GNSS. It's in Grey Hill. And we plan another installation hopefully early next year, and in more on the west side. So I leave it here now, and Elske.
Yeah, but let's finish it first, and
Right.
then we do questions,
Yeah.
right? Did we just skip one or not? No. Okay. So a little bit about what we can learn about other volcanoes. This is a slide of St. Vincent, La Soufiere volcano. I thought maybe some of you have some, at least got some of that information in the news, right here. So in December 2020, this is the crater of La Soufiere. And in December 2020, someone noticed there this pimple, this black thing. The black thing, that's what we call a dome. And that's the first sign of new magma coming to the surface inside the crater. However, by February 21, it had grown to this sort of enormous thing. And then, as we know, in April, there were these big explosions that started to happen. So on this figure here, you see the contour of the dome. So this is how it grew over time. And it was limited in size by this thing here, which was actually the old dome of the eruption in '79. So the dome growth actually took months already. And then it still took some time before it started to explode. So a volcano that starts to reactivate is not something that happens from one day to the next, right? It can, but it's very unlikely here. And we see this also in other volcanoes in this region. It usually takes months. Okay. Then I wanted to show you where you can find more information. So we have this website. On it, there is a link to the live seismograms, so you can just click on them and you can see the recordings live. And there's always the current alert level status, which you can see here. So green is good, right? If we change it, then I'm sure your local government would let you know as well. But you can check, for yourself too, you know, if it's still green or not. And there's also lots of background information. Our work, of course, would never be possible without the help of the government here, Satel, and also all the people of Seba, right? Whenever we're here, everyone is helping us, finding places and doing our work and making sure that we can do our work. So thank you very much for helping us, basically, do our work the way we should be doing it, right? And then now it's time for questions. So thank you.
Sure.
Who had a question? Yes.
About the eruption in La Palma, right? And now they're predicting it might be a landslide.
Right.
And how
Okay.
that's going to affect us. No, don't say but we're high enough. Don't even.
Yeah. No, but I can say
So,
something.
yeah,
So
just.
she's asking about eruption in La Palma, and there's been a theory about a possibility that part of the island may slide into the sea and cause a tsunami. And it's right that this theory has been in the news. However, this theory is already quite old, and more recent work has shown that the volcano is actually quite stable, and there are no big cracks visible or anything, and it's very unlikely that this scenario would happen. So I don't think that the monitoring agency that monitored this volcano, it's in Volcan, they have lots of equipment similar to the equipment that we have here, and they're also spreading the news that, you know, it's not a possibility that's considered very likely that there will be a landslide. Yes, please. Well, yeah, so he's asking about the voice of Columbus, and that he wrote that maybe that he had observed an eruption at Mount Scenery, and it seems to match with the timeline that I showed earlier. Well, of course, if you know where in writing it says that, I would be very interested to have that source so I can read it, and also, of course, it's good information because. You're right, there were other people on the other islands in the Caribbean earlier than there were people here. And I've always wondered, like, why no one, someone must have seen something, you would think so, right? And someone may have written it down, it's just a matter of maybe of finding the right source for it. But, sorry? Yeah, so let me know, drop me an email. Yes?
In the graphs of Seba from like 2020, you could see in like October there were a few dots off. So what
Yeah.
could indication
No, not necessarily. It takes more than that, because of course the first thing, if I see some dots that are off, right, then I check the seismometers, because really what you would expect is that you would start to see signals in all of these instruments, right, and not in just one. But then of course we also know that if there's bad weather conditions or there's other things that you can get these dots that are a bit off, and so yeah, we don't immediately worry, but we then watch it more carefully, right? Yes.
I was wondering, you were describing the surface waves, and are they related to tsunamis, or are they, or is there, what is the
Yeah,
relationship?
repeat the question. He's asking if surface waves are related to tsunamis.
Yeah. No, this is not the case. A surface wave, they really travel along the Earth's surface, but has nothing to do with tsunamis, because tsunamis do occur when there is a vertical movement under the water, which will lift up the water, and then the water wave will travel further on, and then it can come, let's say, to the coastal area. So it is totally unrelated.
So the surface wave is actually traveling on the seabed?
It travels on the surface of the crust, so also under the ocean. Yes.
And maybe what is interesting to add to that is that the data from the seismometers on the island actually are going to the Pacific Tsunami Warning Center, which is the center that's dedicated to observe this region for tsunamis. And so these data are actually contributing to generating tsunami warnings. So if there would be a possibility of a tsunami, the warning would be issued. Also based on the data from here. So, yeah,
The
Eva.
deepest earthquakes were at about 200 kilometers. How deep is the actual crust? How big is that? How far?
Now the crust is not so deep. The crust is maybe around 40 kilometers, and then the mantle starts, what we call the mantle. So, but in the subduction zone, the crust is let's say penetrating the mantle, and goes deeper.
Yeah.
So, yeah.
How far from the surface to the center? Just for my.
Yeah, that's
That's-
difficult to say. I mean, if we can go back to the view of the profiles with the earthquakes, then you can see, yeah,
There was.
then you can see here that again the earthquakes, they go up to a depth of about 200, maybe 250 kilometers, and because at that region, the temperature is so warm that, let's say, the stress within the material, it will be dissipated, and it will
Yeah.
like that.
It cannot
So-
generate an earthquake
Right.
anymore because
Yeah.
it's too sort of mushy,
Right.
ductile, as we call it.
Yeah.
But yeah. All right.
So in one of the first slides you guys showed was that you took samples from the bottom, and that's where you basically dated that it was 400 to 500 years ago
Yeah.
that the last eruption happened. Like any other places where you guys took samples from?
So first to yeah, so he's asking about the samples in the bottom, if there's any other samples that we took. So first of all, these samples were taken by a team from Trinidad, Robol et al. So it's not by us, but before we started our work here, and in total they took 4 samples, but that's very, very limited. It would be nice to in the future do a more thorough search, and now also the way of dating has evolved, so you can do other types of dating. So maybe there's a way to get a better understanding of the history, and especially the history of the most recent eruption. Yeah. Yes, there's a question there. Well, it's the most recent. He's asking if it's true that the first eruption was in 1614, but it's true that the most recent eruption was likely around that time, yes. But there have been many eruptions longer ago, so before that. Is that clear? Good. What is happening with Kikimjeni? Okay, so Kikimjeni, I think it's for those of you that do not know Kikimjeni. Let's see if we can go back to Kikimjeni all the way to Kikimjeni. Kikimjeni is right there, right? As you can see, the triangle is colored yellow, so that means it's at least it's in unrest. Kikimjeni, I think the last eruption was in 2017 that it really erupted, but it's still very active, and it will erupt again. It's trying to form an island, right? And this is eventually it may come above sea level, but I don't think I will live long enough to witness that. Maybe, yeah. Yes.
On the previous slide that you had up, you mentioned that inactive is near Saba. Is that simply because there are no sensors there?
Yeah. Well, there were no sensors there
Right.
for a while
Yeah.
until we started working here, basically.
So you would expect that that area would have been filled in if there had been sensors.
Right. I think the reason is indeed that there are no sensors, let's say, until a couple of years ago. And then it's more difficult to detect the smaller earthquakes. And I think we can fill that gap with the network here. Correct.
Yes. Yes. Yeah, this gentleman is saying that I've never used the word dormant. That is true. I do that on purpose because within the community we try to change to using the word active but quiet, because dormancy may give a false impression of complete sort of, nothing's going on. And we like to explain to the people that yes, it's quiet, nothing is going on, but it's still what we call an active volcano. So you're right, I'm trying to not say dormant, right? Yes.
My other question is completely unrelated to this one, and it's more of a political question that you do not want to answer. Why did it take so long before monitoring of the volcano started?
I don't know. He's asking why it took so long before we started monitoring on the volcano. I honestly don't know. So I joined in 2017, and Reinoud started with the first seismometer in 2006. I guess the answer may be that political mills just take long. It's a slow process. Whenever we want something, it takes time. Fortunately, the volcano gave us the time, right? And we're now, I think with the equipment we have now, we're doing compared to the other islands and what sort of activity they have and what sort of equipment they have installed. We really looked at that, and I think we're slowly getting Saba into one of the best monitored islands of the chain. So we're nearing completion to the monitoring network. We will do some more expansion hopefully next year, but I think already what we have now is very good compared to some of the other islands. So yes.
Do you guys, between yourselves, have bets where the next one's going to be?
We don't say that.
Well, yes.
There was some recent reports of dead vegetation on top of the mountain.
Yes.
That was linked to gas eruptions and possible eruptions. Is there any truth to that?
Thank you, Kai, for that question. Kai is asking about a dead patch on the volcano. It's true that a while ago, more than a year ago, there was a dead patch of vegetation seen on Saba. So, of course, whenever there is such a thing, we need to take it serious, right? We are on an active volcano. So a team of Saba Conservation Foundation went out and they consulted with us, and we checked the instrumentation, didn't see anything there, but nevertheless they went out, they looked at the site, I told them what to look for, they didn't see anything unusual, and then we kept monitoring it, also using a drone, and we saw the vegetation growing back, and that's definitely a good sign, because if it was the volcano, we would have expected that this patch would enlarge and it would kill more vegetation, which it didn't do. So it's very good if you observe such a thing that you let us know, and then we'll take action, right? But in this case, it was definitely nothing to worry about. Yes?
It might be outside the scope of your research, but do you have an idea of the scale or size of the magma chamber that's below Saba?
That's a good question. Yeah, we don't have very much information about that, but I have a PhD student in Canada who's actually looking at geochemistry of the rocks. She came here a year ago or 2 years ago, collected rocks. She took them to Canada and she's analyzing them, and hopefully looking at geochemistry we may be able to answer that a bit better. Yeah. Was another question there? Yes? The crater, you mean the crater? Well, the crater is on the top. That's He's asking where the crater is. The crater is on top, and that's right. There was a theory a while ago that the crater was maybe in the bottom, but that I think later scientists said that no, the bottom is more like a slide. So the sides are fractures, and some material went down into the sea maybe, and that created the sort of flatness of the bottom. So there's no real evidence that the bottom itself is the crater. Yeah. But the thing on Seba is that you see all these domes, right? And each of these domes in history very likely had material coming out. So each of the domes is like a little baby crater, little baby volcanoes. Yeah, all of them. And they're all very old, but all of them are little, so yeah. Any other questions? It's very hard to see you guys. No? All right.
Thank you everyone for coming. As a reminder, please move to the back. Your dinner reservation should be prepared shortly. We're going to move some chairs around. Thank you, Eco Lodge, for hosting. You guys are welcome to stay for dinner and drinks. Yes, a big round of applause. Thank you, Elske and Reinoud. And we'll see you later.
Thank you.
That was super interesting.
It was. Yeah, good to hear. Thank you. So, Elske, jouw water. Yeah, it is.